Welcome back, and today we're going to be solving more Leetcode. Today we're going to solve the Leetcode medium, 2 integer sum 2. And more importantly, I'm going to show you why this problem is different from the original 2 sum first before we jump into it, and why that difference completely changes the approach. So let me just start by clearing that up right now. In the original 2 sum problem, if you remember, the array was not sorted. Because of that, the solution we used had a hash map. But here in 2 integer sum 2 or 2 sum 2, the array is sorted for us. It's already sorted. So that single difference is what allows us to use a 2-pointer technique, and why we use it in 2 sum 2. You'll see me explain that shortly. And also, let me just explain why we can't use 2 pointers in the original 2 sum. In the original problem, the array isn't sorted. So if we have 2 pointers, moving left or right doesn't tell us anything useful. So we don't know if moving a pointer increases or decreases the sum. So that's why we use the hash map. That's just to clear that also up. But I'm assuming you guys knew that already. So now let's just jump into the problem now after clearing that up. So here's the problem in plain terms. So we are given a sorted array of integers and a target value, very similar to 2 sum. And there's exactly one pair of numbers that adds up to the target, and we need to return their indices one indexed. One indexed means, so how in an array the first element index is 1 and the second one's first one is 0 and the second one's 1. And one indexed, the first element is 1, and then obviously the second one is 2. So that, just to clear that up, it's pretty simple, and it explains it in the problem as well. So since the array is sorted for us already, the smallest value is on the left and the largest is on the right. So that fits 2 pointers perfectly. So let's say we just have an array here. We have 1, 2, 3, 4. So we would place one pointer at the beginning and one pointer at the end. So let's call one of the pointers the left pointer at the beginning and the right pointer at the end. And now for the core logic, how we would do this is we would iterate through, and at every step we would look at the sum of the 2 pointers. And from there we could just adjust. So you would add the 2 pointers and take the sum. If the sum is too small at those 2 pointers, that means we would need a bigger number. And that would mean we would just move the left pointer to the right to get a bigger number, because it's from increasing. Remember, it's sorted, the array. And also the same thing. If the sum is too large, then that means we need a smaller number, right? And that means we can just move the right pointer to the left to get a smaller sum. And obviously we're comparing the sum to the target. That's what I was talking about before. So this only works because the array is sorted. Just remember that. So now let's just walk through this example here real quick. So we have the left and right pointer here. So step 1, the first iteration, left pointer is at 1, right pointer is at 4. The sum of these two, 1 plus 4, 5. That is too big. That is bigger than our target. 5 is bigger than 3. That means we have to move our right pointer to the left 1 so we can get a smaller sum. So now let's go the second iteration. So now the pointer is at 3, the right pointer. The left pointer is still at 1, the right pointer is at 3 now. 1 plus 3, the sum of that is 4. 4 is still bigger than 3, which is our target. So now that means we move the right pointer to the left 1 more. And now our right pointer is at 2. So now the sum of the right and left pointer is 3, which equals our target. And now we found our pair. So this is how the logic works for this two-pointer solution. So this is really efficient because each pointer only moves in one direction, and we never backtrack, and we never check the same pair twice. So this runtime would be big O of n, and the extra space is constant because we don't have like an extra array or hash map or anything. So now let's code this exactly the way we described it. So let's go here now. Okay, so now we're here. So now at the beginning, at every two-pointer problem, we want to initialize our 2 pointers. So let's initialize our left pointer and our right pointer. So obviously our left pointer will start at the beginning of the array 0, and then the right will start at the end. So length of numbers -1. And then obviously we'd have a while loop, and this loop runs until the pointers meet. So because we don't want them to cross. So while left is less than right, we don't want them to cross, and once they cross, there's nothing else, like there's nothing for us to check. That means we've gone through the whole thing once they cross. So now we want to get the sum at each pointer. Remember what we did back there just a moment ago? So at each step, we compute the sum of the two values the pointers are looking at. So we can do this, we'll call it current sum equals numbers at the left pointer position plus numbers at the right pointer position. So this will give us our current sum at every step. And now this is where the conditionals come in. So if our current sum is smaller than our target, right? Then if the sum is too small, we move the left pointer to the right to increase the sum. So we would increment the left pointer by 1. And then we need another one, if, another conditional. Now this is for if the sum is too small. So, or if the sum is too large, sorry. So if current sum is more than target, that means we need to decrease the sum. So we move the right pointer to the left to decrease the sum. So we decrement the right pointer by 1. And then we need a last one, last conditional else. So if we reach the end here, that means if it goes past these two conditionals, if they don't like meet, if they're not true, then that means we're on the last one. That means we found our target. So when the sum matches the target, we return the indices. So return just the left pointer plus 1, because remember it's 1 indexed, and then the right pointer plus 1. Yeah, okay. And like I said, we add 1 because the problem uses 1 based indexing, not 0 based. So now if I run this, if I didn't make any mistakes, the test case should pass. Yep, there you go. Let me just submit it here. And yep, there you go.